Let us begin with a fact that feels a little strange the first time one hears it, and perhaps even the second or third time. A Fourier series can approximate a function remarkably well, and yet near a jump, near a sudden break, it can still behave in a way that looks almost stubborn. It can ripple. It can overshoot. It can seem to refuse to settle down in a neat and obedient way we might expect. And this is one of the most beautiful and subtle parts of the subject. So tonight, or now, or in this quiet moment, let us think slowly about that phenomenon. Let us think about why an approximation can be globally excellent and still locally peculiar. Let us think about why smooth waves, when asked to imitate a sudden jump, do something curious at the edge. This is the Gibbs phenomenon. Let us start gently. When we speak about a Fourier series, we often speak as if we already have the whole object in front of us, as if the infinite expansion is simply there, complete and finished. But in practice, and also in thought, we do not usually begin with the full infinity. We begin with the finite approximation. We take only the first few wave components. Then perhaps a few more. Then more again. These finite pieces are called partial sums. It is worth repeating that phrase in a quiet and practical way. A partial sum is the approximation we actually have when we stop after finitely many terms. It is not yet the entire infinite series. It is the version we can draw, compute, listen to, or use. So whenever we discuss approximation in a real and tangible sense, we are very often discussing partial sums. And each partial sum is built from smooth oscillating waves. Each added wave refines the picture. Each new frequency gives us a little more detail, a little more flexibility, a little more power to match the target function. This is the hopeful side of Fourier series. By adding waves, we can reproduce shapes that at first seem far removed from pure oscillation. Flat regions, sloping regions, repeating corners, even functions with abrupt jumps can all be described through these wave ingredients. But the way this description works is not always perfectly gentle at every point. Let us pause and reflect on that. A Fourier approximation is not like placing one little correction exactly where it is needed and nowhere else. A wave spreads its influence across the whole interval. It is global. If you change one coefficient, you are not only changing the approximation near one point, you are changing it everywhere. That is one of the central ideas here. Waves are not local patches. They are whole domain objects. And because they are whole domain objects, when they try to capture something sharply local, like a jump, they do not do it in a purely local way. They lean into the jump from both sides. They swing above and below. They create oscillations. This is already the beginning of the Gibbs phenomenon. Now let us imagine a periodic function that has a jump. On one side of a point, the function sits at one level. On the other side, it suddenly moves to another level. There is no gradual transition. No smooth ramp. Just an abrupt change. If we try to approximate this function with a partial sum of a Fourier series, what do we see? Far from the jump, the approximation often looks very good. It may trace the flat pieces well. It may follow the general shape with increasing accuracy as we add more terms. The more terms we include, the better the approximation becomes in many places. But near the jump, something else happens. The graph begins to wiggle. As it approaches the jump from one side, it rises too much or falls too much. Then on the other side, it swings back. Instead of passing calmly into the new level, it oscillates around the discontinuity. And one of these oscillations is especially striking. The approximation rises above the value we might naively expect, or it dips below it. There is an overshoot. It is worth repeating, near a discontinuity, the Fourier partial sums do not simply blur the jump in a quiet way. They develop oscillations, and these oscillations include a persistent overshoot. At first, a student may think this is only because we have not taken enough terms. That is a natural thought. One imagines that once enough frequencies are added, the approximation will eventually stop overshooting and settle perfectly. But that is not what happens. As we take more and more terms, the oscillations do become more compressed. They get squeezed into a narrower region around the jump. In that sense, the approximation improves. The disturbance becomes more tightly concentrated. Away from the jump, things become very accurate. Even near the jump, the problematic behavior occupies a smaller and smaller neighborhood. But the height of the overshoot does not go all the way to zero. That is the astonishing part. The width of the oscillatory region shrinks. The ripples crowd closer to the jump. Yet the maximum amount by which the approximation overshoots remains, in a certain sense, stubbornly present. It does not simply fade away with more terms. This persistent overshoot is what we call the Gibbs phenomenon. Let us say that once more in a slightly different way. The Gibbs phenomenon is not merely that there are oscillations near a jump. It is that these oscillations have a characteristic overshoot whose amplitude does not vanish completely as the number of terms increases, even though the oscillations themselves get confined to a smaller and smaller region. This is a subtle statement, and it is easy to lose the thread, so let us pause and summarize. We have a function with a jump. We approximate it using partial sums of its Fourier series. Each partial sum is made from smooth waves. These waves cannot reproduce a jump in a perfectly sharp local way. So near the jump they oscillate. As they add more terms, the oscillations are squeezed closer to the jump. But the overshoot height does not disappear entirely. That is the core picture. Now, why should this happen? Not in a symbolic sense and not in a technical proof, but at the level of understanding. A jump is abrupt. A Fourier partial sum is smooth. And here smooth does not merely mean visually pleasant. It means that the approximation is assembled from ingredients that vary continuously and rhythmically. There is no single finite combination of these smooth waves that can create a perfectly abrupt break without compensation nearby. To produce a rapid transition, the approximation must use many frequencies together. And when many frequencies cooperate to create sharp structure, oscillation appears naturally. This is a general lesson in harmonic analysis. Sharp localization and oscillation are deeply connected. The more abruptly we try to force a transition, the more ringing we tend to see nearby. You can think of it almost like trying to recreate a sudden clap using only pure tones. The tones can combine to mimic the sharp event, but the combination has side effects. It spreads energy around the transition. It creates a little ringing structure. The approximation is trying very hard to reproduce something discontinuous using components that are inherently smooth and extended. So the overshoot is not a sign that Fourier series are broken. It is a sign of the tension between the object being approximated and the tools doing the approximating. That is an important philosophical point. This is not a failure of the method. It is a feature of the method when the target has abrupt change. It is worth repeating because it matters. If one only looks at the overshoot, one might conclude that Fourier series are defective near discontinuities. But that would be too crude a judgment. The series is telling us something honest. It is telling us that representing a jump by smooth global waves comes with a price. The price is a local oscillatory artifact. And yet, globally, the approximation can still be extremely good. This contrast between local imperfection and global success is one of the deepest things to absorb. Let us stay with that for a moment. Suppose you look at the approximation over the whole interval, not just at one tiny neighborhood of the jump. You may find that it matches the function extraordinarily well almost everywhere. The regions away from the discontinuity may be captured with great precision. The total error, measured in an average sense, may become very small. Even visually, except for a tiny zone near the jump, the approximation may look nearly perfect. So what should we conclude? We should conclude that approximation is not a single idea. There are different ways for an approximation to be good. A function can be approximated well overall while still displaying local artifacts near a special point. If we focus only on the worst pointwise behavior, we may miss the larger success. If we focus only on the overall success, we may miss the delicate local structure. Fourier analysis teaches us to hold both truths at once. Now there is another important fact, and this one concerns what the Fourier series actually converges to at the jump itself. When the target function has a jump, the Fourier series does not converge there to the left-hand value alone, nor to the right-hand value alone. Instead, it converges to the midpoint between those two limiting values. This is a remarkable and very elegant result. So at the discontinuity, the series chooses the average of the two sides. Let us restate that carefully. If the function approaches one value from the left and another value from the right, then the Fourier series, at that jump point, settles not on either side individually, but on the value halfway between them. This can seem surprising at first. Why should the midpoint appear? At an intuitive level, the Fourier series is balancing the two sides. It is not able to reproduce the actual jump value in a literal, point-by-point sense using finite smooth oscillations, so in the limit it lands at the symmetric middle of the two neighboring states. The series reflects both sides of the discontinuity, and the midpoint becomes the natural compromise. Again, this is not a defect. It is part of the correct convergence theory. Let us pause and reflect. Away from a jump, the Fourier series of a reasonably nice periodic function often converges to the function value itself. At a jump, it converges to the midpoint of the two one-sided limits. And near the jump, the partial sums exhibit oscillations with persistent overshoot. These three facts fit together. They are not separate curiosities. They are different faces of the same phenomenon, the interaction between discontinuity and harmonic approximation. Now, one might ask, if the overshoot does not vanish, then in what sense are the partial sums improving? This is a very good question. They are improving in several senses. First, away from the jump, they are becoming more accurate. Second, the oscillatory region becomes narrower. Third, many global measures of error improve steadily. So the approximation is sharpening, even though one particular local feature remains. Perhaps the easiest mental picture is this: the error does not disappear uniformly, but it becomes concentrated. That phrase is useful. The error becomes concentrated. Instead of being spread broadly across the interval, the difficult part of the approximation gets trapped close to the jump. The approximation is therefore becoming more and more faithful almost everywhere except in an ever-shrinking neighborhood. It is worth repeating that because it helps reconcile the paradox. The overshoot persists in height, but the region where it lives shrinks. So there is no contradiction between persistent local ringing and improving overall approximation. Now let us return to the partial sums themselves, because they are central to the story. A partial sum is not the final infinite object. It is a finite truncation. It uses only the first portion of the frequency content. And whenever we truncate an expansion of this kind, we impose a limit on how sharply the approximation can respond. Finite frequency content cannot produce arbitrary abruptness without oscillatory side effect. In signal processing, in physics, and in many branches of analysis, this is a recurring theme. Sharp edges provoke ringing. So the Gibbs phenomenon is not only a fact about one textbook graph. It reflects a broader principle. Whenever smooth oscillatory modes are used to approximate sudden transitions, one should expect this kind of behavior. That is part of why the subject is so rich. A single example opens onto a very general idea. Let us pause and summarize again, slowly. A Fourier series decomposes a periodic function into waves. In natural use, we work with partial sums, meaning finite collections of those waves. Each added wave improves the approximation, but because waves are global and smooth, the improvement is not perfectly local. Near a jump, the approximation oscillates. Those oscillations include an overshoot. As more terms are added, the oscillations are squeezed closer to the jump. But the overshoot height does not fully vanish. At the jump point itself, the series converges to the midpoint of the left and right limits. So the method succeeds in a deep and meaningful way, even though our first intuition may have expected a cleaner local fit. Now there is also a psychological lesson here, and perhaps even a mathematical one that goes beyond Fourier series. We often imagine that better approximation should mean better behavior at every point in the same simple way. We imagine a monotone story, more terms, more accuracy, less error everywhere. But mathematics often teaches us that infinity is subtler than that. Improvement can happen in one sense, but not another. Convergence can hold globally, or on average, or pointwise almost everywhere, while still failing to satisfy the most naive geometric expectation at a special set of points. The Gibbs phenomenon is a gentle entrance into that deeper maturity. It teaches us not to trust only immediate visual intuition. It teaches us to ask, in what sense is convergence happening? Where is it happening? What kind of error is shrinking? What kind of error persists? These are sophisticated questions, and this example invites them naturally. It is worth repeating that the Fourier series is powerful not because it avoids every visible artifact, but because it captures the essential structure of functions with extraordinary reach. It handles smooth behavior beautifully. It handles rough behavior surprisingly well. And even where it produces ringing, the ringing is itself understandable, quantifiable, and mathematically meaningful. So one should not look at the Gibbs phenomenon with disappointment. One should look at it with respect. It is a shadow cast by a very powerful idea. Let us make the central image calm and clear one last time. Imagine a jump. Now imagine approximating that jump with more and more smooth waves. The approximation gets better overall. Far away, the fit becomes excellent. Near the jump, ripples appear. Those ripples get narrower as more waves are added. But the first overshoot remains of noticeable height. The exact jump is never reproduced by a finite smooth combination without this local ringing, and in the infinite limit, the series settles to the midpoint at the discontinuity itself. This is why the approximation overshoots. Not because Fourier series fail, but because abrupt change is being expressed through smooth oscillation. The overshoot is the visible signature of that translation. Let us pause and reflect. There is something almost philosophical here. Infinity often keeps its promises, but not always in the form our first intuition expected. Fourier series does converge, but at a jump it converges to the midpoint. The approximation does improve, but not by eliminating the overshoot height. The local disturbance remains, while the global description becomes more and more faithful. So the subject asks us to become more precise in our expectations. Better does not always mean flatter. Convergence does not always mean uniform visual com. And an approximation can be profoundly successful, while still preserving a small but persistent local irregularity. That is one of the reasons Fourier analysis is such a beautiful chapter in mathematics. It is concrete enough to draw, subtle enough to surprise, and deep enough to reshape intuition. Now let us end slowly, gathering the ideas together. We began with the strange fact that a Fourier series can approximate a function extremely well and yet behave oddly near a jump. We introduced partial sums as the finite approximations we actually use. We noticed that each added wave improves the fit, but because waves are smooth and global, they do not repair a discontinuity in a purely local way. Near the jump, oscillations appear. This oscillatory behavior is the beginning of the Gibbs phenomenon. Then we saw the central surprise. As more terms are added, the oscillations are compressed closer and closer to the jump, but the overshoot does not disappear completely. Its height does not fully vanish. This is not a breakdown of Fourier analysis. It is a natural consequence of approximating abrupt change using smooth waves. At the jump point itself, the series converges to the midpoint of the left and right limiting values. And across the whole interval, the approximation may still be extraordinarily accurate, even though a local artifact remains. So the final lesson is gentle and important. Fourier series are powerful. They reveal hidden frequency structure inside functions. They approximate with remarkable success. But infinity is subtle, and sharp edges leave traces. The overshoot near a jump is one of those traces. It reminds us that mathematics often works beautifully without working in the simplistic way we first imagine. And perhaps it is worth carrying with us. A good approximation may still have a ripple, a powerful method may still reveal its limitations honestly, and understanding deepens when we learn not only what works, but how it works, and why it looks the way it does. It is worth repeating, one final time, that the Gibbs phenomenon is not a flaw to be feared, but a feature to be understood. And with that, let the picture settle: smooth waves, sudden jumps, narrowing oscillations, persistent overshoot, midpoint convergence, and the quiet realization that mathematics is often more delicate and more beautiful than first intuition suggests.